Hello everyone. Good night. Hello, buenas noches a todos. Almost there. Okay, so I will be speaking in English this time. Yes. Hello everyone. This is one more edition of the VTuber the Science VTuber Symposium. This is, I believe, maybe the fourth or third one. I can't exactly remember, but okay. So, anyways, for those who don't know me, I am Doutor Ekelus. I am the first Brazilian scientist VTuber, and I do this symposium every year. This year I've done with some Brazilian members from some VTubers from the Brazilian community, and now we have the International edition with some VTubers from abroad. So, yes, the symposium happens every year. It's a pet project of mine, and I am very glad to be making it and also maintaining it every year. And yes, so this time around we have new guests, never shown in the symposium before. So with that, I would like to begin with Millennium. If you please could introduce yourself.
Hi, I'm Millennium Isekai Mask Knight Empress Scientist. I stream on YouTube, some Genshin Impact, Tekken 8, Pokemon, and I do jumping jacks as well. And yeah, now we are exploring the science side too, because before I did biochemistry and molecular biology streams as well. So that is the thing that I do.
Thank you very much. Okay, so next one is Rico. If you please could introduce yourself.
All right. Hey everyone, I'm Rico Sampre RN. I'm the VTuber RN educator and registered nurse in real life. So you heard that correctly. I am an actual practicing registered nurse in the state I live in. I work in outpatient dialysis, but just because I work and on the field and working with patients doesn't mean I still don't have an interest in science. So today I hope I can convince y'all to think about how nursing is still very much a scientific discipline.
Nice, thank you very much. I already see Ursha is doing my job for me. Thank you very much. But okay, yes, Ursha, it's your time to show. Your time to show who you are. There we go.
Hello, my name is Ursia Cientia. I'm a berry-friendly scientist doing his very best. I am a variety streamer. I stream here most on Twitch. And outside of my streaming, I am a professional geologist. Been working now for about 7 years, both in hydrogeology and environmental remediation and monitoring. So
Okay.
thank you for having me. It's very nice to be here. I'm excited.
Oh, thank you for being here. I will thank you guys later. But just for continuing the presentations, Nico, can you please introduce yourself?
I'm Nicoplasm Nico, aka Nico, or you can call me Nico. I'm the bacteria scientist VTuber. I stream on Twitch a variety of games, usually strategy games, but I also make shorts on YouTube that are science focused and they cover all sorts of microbiology, bacteria, and just random cool science facts if you want to ever check those out. I'm really happy to be here and talk about science and also bacteria and show you guys how bacteria is part of the food science field.
Okay, nice. Okay. So before we begin the presentations and the actual symposium, I have again to thank all of you for being here, for accepting the invitations, and also thank everyone who is in the chats, both in Twitch and also YouTube. Thank you very much for being here. This, like I said, this is a pet project of mine, and I'm very proud of it. And I just hope to keep going with it and keep making it more and more professional every time. So yes, thank you very much for all you guys for being here, and yeah. So let me just a little bit of an edit in here. Yes. Okay. Millennium, I think when you
Yes.
are ready to begin, you can share your
Okay,
screen.
let me share my screen. Clicking the buttons here, and then let me just check how it is on the other end as well. Clicking here, and then is the window capture working? The Discord is here.
Second.
Nope, you popped
Just,
out on
yeah,
another
there we go.
screen. Discord, PowerPoint. I'm checking also on my, because I'm streaming it as well.
Yeah.
PowerPoint
Sure.
presentation .exe. Okay, it's there. And sorry, 1 second. PowerPoint stream, stop stream. Is it there? Go here. Okay, it's there. It's there. Just lower this part. Alt. Here, there we go. And the screen go down. Give me like 2 seconds.
Not a problem, Lenium.
Not a problem. No worries. In the
Here.
meantime, just to speak with everyone in chat, you can ask questions if you want. I will be asking them in the end of the presentation, but please feel free to ask any questions you have in the presentations.
Yup. And it is, am I here? There. And I'll move my PowerPoint there because I realized if I click the button, it's saying that I am not there. Okay. I can see it on my end. Can you see it? Can you see the slides?
We are seeing an art of of your
A picture, right?
yes, a picture.
Okay, that's correct. Like a manga picture. Like a manga picture, do you mean?
Oh yeah, yes, a manga picture. That's it.
Okay, that's the right one. All right. Okay, perfect. Yeah, this is a great demonstration because I am discussing how your heart goes, Doki Doki, and I have a heart rate monitor actually right now, and it's live.
Oh,
There we go.
Your heart rate
So,
is going live
yeah.
right now? What are you reading right
Yup.
now? I gotta know.
It's at 111 from 80.
111?
Oh my
Yes.
goodness.
So I'm
Are you
discussing
okay?
how
Are
the
you
heart
nervous?
beats. Yeah, like so that's the thing. But hi,
so
I'm
exciting.
Millennium. Isekai Mask Knight's Emperor Scientist, and today I will be talking about how the heart beats. So that first 2 to 3 minutes was indeed a great demonstration that the heart does beat, and now it's at 117. But yep, have you ever felt your heart suddenly go doki doki? Maybe when you're nervous, or when you are excited, or when you're watching your favorite anime series. In shoujo, doki doki is a Japanese onomatopoeia for the sound of a fast beating heart, aka a heart, like the heart pounding. So today I want to answer this question: how does your heart beat? And the answer is not electricity. It is tiny doors called ion channels, such as this one. It's calcium moving inside cells, and it's muscle fibers moving like it's squeezing in perfect timing. So today I will strive to explain how the heart beats step by step in a hopefully easy to digest manner. So, first, the heart is a muscle. It's about the size of your fist, and it sits slightly to the left in your chest. And its job is simple: it pumps blood, okay? Blood carries oxygen to every part of your body, and if the heart stops pumping, oxygen stops moving. So, every beat matters. Now, let's zoom in. The heart is a muscle made of 4 chambers, the 2 atria at the top and the 2 ventricles below. Blood enters through the heart through the right atrium here, and then from there it passes through the tricuspid valve like a gate into the right ventricle. And the right and left here, it's not like the picture. You imagine you're looking at the patient. So that's why this is the right atrium, and then go to the right ventricle. And then the right ventricle pumps blood by passing through the pulmonary valve into through to the pulmonary artery to the lungs. And in the lungs, the blood picks up the oxygen and releases carbon dioxide. And then the oxygen-rich blood would then return to the heart through the pulmonary veins. And then it enters the left atrium. Okay? Then it moves through the bicuspid valve, another gate, into the left ventricle. And then the left ventricle is a very strong chamber. It's actually the strongest chamber. And it pumps blood through the aortic valve, through the, it's a semilunar valve, and into the aorta. And then it would distribute the oxygenated blood throughout your entire body. Okay? So that's why that flow is important. Essentially, the atria receives the blood, and the ventricles pump the blood out. Now, here's another important part. The atria contracts first, and then the ventricles contract next. If everything is squeezed at the same time, blood would not move efficiently. So you need to time it well. When the ventricles contract, that is ventricular systole. The atrioventricular valves would then close. And that closing is the first heart sound, the lub. And then when the ventricles finish pumping and they begin to relax, you enter a thing called the diastole. The semilunar valves close, and that closing is the second sound, the dub. So every time you hear the lub dub, that is the sound of the valves closing at the correct time. Lub is the ventricles contracting, and dub would be the ventricles relaxing. And yeah, the heart is made out of cardiomyocytes, special muscle cells, and each cardiomyocyte can contract, meaning it can shorten and squeeze. But the important part is that these cells are connected to each other through intercalated discs, which allow the electricity to move from one cell to the next. And that's why the heart doesn't beat normal, like randomly. Hopefully it beats normally for you. But yeah, that's why it doesn't beat randomly. It beats together. And every beat starts with electricity. Now, here's the key idea. Every heartbeat starts with electricity, right? It is in a region called the sinoatrial node, the SA node, and this is the natural pacemaker. SA nodes are special because they slowly depolarize or become more positive on their own, and they have ion channels that leak positive charge inward. This gradual rise would reach a threshold, and then an action potential would fire, and then this signal spreads across the atria, the ones at the top. It reaches the AV node, the atrioventricular node, which delays the signal a little bit because this delay allows the atria to finish contracting or squeezing before the ventricles would start the contraction. After the AV node, the signal travels quickly through the His-Purkinje system into the ventricles, and this causes the powerful ventricular contraction. So essentially, without electricity, there is no heartbeat. And now regarding the ion channels I mentioned earlier, these are the tiny doors, because how would the electricity move inside the cell? Well, yeah, it moves through the tiny protein doors called the ion channels, and these channels allow charged particles called ions to move in and out. And the 3 most important ions for the heartbeat are sodium, calcium, and potassium. The sodiums would rush in, like it helps start the electrical signals. The calcium entering the cell would strengthen and maintain the signal. And then the potassium leaving the cell helps reset everything so you can have a new beat. And these channels open and close in a very precise manner because if the timing is correct, the rhythm is smooth. If the timing is wrong, the rhythm can break. And now we reach another important concept called the ECC, or the excitation contraction coupling, where excitation would be the electricity part, contraction is the squeezing part. So here's what happens. You have the electricity traveling along the cardiomyocyte membrane, and that signal moves down the T tubules, this little V shape here. And then that brings the signal inside the cell. And the T tubules have the special calcium channels called the L-type calcium channels. And when the signal reaches them, they open, and a small amount of calcium enters from the outside. But here's the key, that amount of calcium is not enough to cause a full contraction, but instead it would act as the trigger. Because inside the cell, you have the storage compartment. You have the storage compartment for calcium called the sarcoplasmic reticulum.
Very, very much intertwined.
Wait. And inside the cell is a storage compartment for calcium called the sarcoplasmic reticulum. Yeah, I mentioned that one. And on this one, you have the ryanodine channels on your sarcoplasmic reticulum, the RYR. And when the first calcium enters through the L-type channels, it would activate your ryanodine receptors, and that would release more calcium. So that's why it's the calcium-induced calcium release. If when you receive the first set of calcium, it would tell more calcium to happen. So now you have a ton of calcium. These calcium would bind to a protein called troponin, and this allows the muscle fibers, your actin and myosin, to slide past each other and then cause the cell to shorten. So when millions of those heart muscle cells shorten at the same time, your heart squeezes. So to sum that part up, electricity opens the L-type channels, calcium activates your receptors, they release more calcium, and boom, contraction. And so ECG time, the doctors can actually see the heart's electricity. It's called, and that's called an electrocardiogram. An ECG does not record the squeeze, it records the electrical activity that happens before the squeeze. So remember, electricity comes first, contraction comes after. And here you have the P. This is the P, Q, R, S, and T. The P wave is the small first wave, where this is the electrical activation spreading through the atria. Right after the first signal, you have the atria contracting, pushes blood into the ventricles, and you get the systole. Then the QRS complex, this fancy thing in the middle, this would be the electrical activation of the ventricles. Because the ventricles are bigger and stronger, the signal is way larger. And immediately after the QRS complex, you have the ventricles contracting. And this is the ventricular systole. When the blood is pumped out to the lungs and the rest of the body. And then you have the T wave, or the ventricle, because after the ventricles contract, they should relax. And this is the diastole, the relaxation or filling part. So the T wave is the ventricular repolarization, where the potassium channels I mentioned earlier would help reset the cells. So after repolarization, the ventricles relax, blood flows back in, and the heart refills. So that is one heartbeat having two phases, the systole and diastole, aka the contract and the relax part. Before systole can happen, there should be electricity, and after systole, there must be a reset of the electricity. So when your heart goes doki doki, it's not just emotion, it's electricity moving through ion channels, it's calcium rising inside your cardiomyocytes, and it's muscle fibers sliding in coordination. Your heart beats about 100,000 times a day, and each beat is a very carefully timed chain reaction. So next time you feel doki doki, remember it's science working inside of you. I am Millennium Isekai Mask Knight Empress Scientist who streams Genshin, Palworld, Pokemon, Tekken 8, and more on YouTube. And thank you for listening. Yay!
Yeah.
Awesome. Thank you for the presentation. Very good.
Yay.
Yes. Thank you.
Okay. So Yes, I have a few questions. Actually, I have one. Since you are wearing a heart rate monitor or something like that, uh, can you speak a bit on how the emotional states modulate cardiac activity? Can you please
That
say
part
something?
would be, we can hear you. So it would be the with the autonomic nervous system, aka like with your, because it, for example, your amygdala would detect like fear or threat, and then you have the hypothalamus, right, converting those into autonomic output. So it's your brain, emotions, and your heart talking to each other. That's also where like the fight or flight part, because that is activated like when you are in stress, fear, anger, excitement. And then you also have, if you are resting or digesting, that is the parasympathetic nervous system. And with that one, your SA node, the one I mentioned earlier, this is where emotional stress would come in. Because if you're stressed, you have a thing called the CAMP. It's in one of the different the what's that called, the cascading signals. And if the CAMP increases, you have the faster depolarization in one of the flows I mentioned earlier. So that's where they're like because like stress pacemaker, like gets activated more, and you have which leads to having a faster heart rate. And if you relax, then you have a slower heart rate. Hopefully that answered the question.
Yes, it does. It does. Thank you. I have
Thank
one
you.
more question from Void in chat. What causes a heart attack? Too much electricity running through the heart, maybe?
Mm, Heart attack would be, let me see, because it is like a sudden thing, right? It's not necessarily at too much electricity. It's more of like a blocked blood flow. So it's, and just to clarify, that one is the MI, the myocardial infarction, and it happens when the blood that's supposed to go like the blood flow to the part of the heart muscle, okay, like let's say one of the top, the right atrial area. So yeah, if it's suddenly blocked, maybe by a clot, again, it's a muscle, so it needs oxygen, and that's when the heart muscle cells begin to die. And that is the most like cause of a heart attack. It's not, the electricity isn't necessarily the cause of the heart attack.
Okay.
Oh, but
Yep.
it could cause, oh sorry, like arrhythmia. So maybe that one could be linked. Like arrhythmia would be the either ventricular, like the AFib or vent fib, where it's beating too fast or irregularly. Technically irregularly, could be too fast or too slow, because you have bradycardia being slow and then tachycardia being the too fast version. So that is where the electricity part comes from.
Okay.
Y-
Okay, thank you for
Mind if
the...
I chime in?
Oh, yeah, sure. Feel
Yes.
free.
So, I think your chatter, Doc, actually I think what they're looking for is actually cardiac arrest. So that's when the
Yeah.
heart can't sustain a rhythm that can support life. Period.
Mm,
So electricity can cause that, but there are also other reasons that could also happen.
okay, I see.
Thank you, Rico.
Thank you. Thank you.
Yeah, of
Yes.
course.
Thank you both. Yes. Okay, last question. I believe we have time for it. Last one from Sidian. How does circulation work in the heart muscles themselves? So how the oxygen would pass through the muscles from the
Ah,
heart?
1 second. Let me go back to one of the. I have that one in the slides. It was this part. So This part would be you go right atrium, right ventricle, and then you get that blood would go out to the lungs, and it would pick up the oxygen from the lungs, and then go back to the heart, and boom, from the aorta, that's where it would go to the other parts of the body. So that is how it would the talk, quote unquote, talk to the lungs to grab more oxygen to deliver to the other parts of the body. So that's why the heart is important, like as a pump.
Yeah, I believe they were asking about the heart is a muscle organ, right? So he's
Yes.
asking about how the oxygen would get to those muscles, to the muscles of the heart itself.
You want me to explain?
Oh yeah. Just to make sure I understand right.
This I don't mean to interject. But yeah, for your chatter, there's these arteries coming from the heart that goes to itself to feed blood into the muscles called the coronary arteries. So essentially, when the heart pumps, those arteries pump the heart to the heart itself. So and then it goes after it feeds to the muscles, it goes to the coronary veins and then back into the pulmonary artery, which pulmonary artery to reoxygenate said blood. So that's how the heart gets oxygen.
Itself, yeah.
Yes. Thank you very much. Thank you, Rico. Thank you, Millennium, for the presentation. Very, very good.
Thank you.
Okay. So next one is Rico. If Rico would begin your presentation.
Of course. Let me go ahead and share my screen.
There we go.
And what bam.
Gonna set you up.
Y'all see it?
Just a second.
Yes,
I'm gonna
you
set
are.
it up.
Okay. All right. So everyone, my presentation today is about nursing as STEM. So imagine this. I want you to imagine something. It's 3:17 a.m. Hospital hallway is dim. Monitors are humming. An IV pump alarms softly. In one room, a patient's oxygen saturation drops from 94% to 80%. A nurse notices, not because someone told them, but because a protocol popped up. Not because a protocol popped up, but because something felt off. They look at the EKG. They notice the respiratory pattern change. They mentally run through possibilities: atelectasis, pulmonary embolism, fluid overload, medication effect. They increase oxygen, reposition the patient, reassess lung sounds, review labs, evaluate fluid balance, and anticipate provider orders. Their work prevents a crisis before it escalates. Now, let me ask you something. What discipline were they practicing in that moment? Compassion, yes, but also consider pathophysiology, data interpretation, predictive modeling, systems thinking, qualitative assessment. In that moment at 3:17 a.m., that was STEM. And that moment happens thousands of times per night across the United States. And today, I'm here to say nursing is STEM. So, what does STEM mean? We use the word STEM often. According to Brown et al., STEM disciplines are defined by the integration of scientific principles, technical application, empirical reasoning, and systematic problem solving. Not tradition, not gender dominance, not public perception, methodology. If a field applies biological and physical sciences, relies on quantitative reasoning, integrates technological systems, uses engineering style problem solving, and produces measurable outcomes, then it qualifies as STEM. So the question is not, does nursing feel like STEM? The question should be, does nursing meet the criteria? So let's walk through it. The debate and the cultural narrative. When Hedgecock wrote in Forbes in 2016 that even experts disagree on whether nursing is STEM, it exposed something deeper. Green and John argue that the debate itself reveals how we culturally categorize knowledge. For decades, nursing has been framed primarily as a caring profession, and caring, historically, has been feminized. And feminized labor has historically been undervalued in technical hierarchies. So here's the uncomfortable question. If nursing were male dominated from its inception, would we still be debating whether it is technical, or would we simply assume it was? Because no one debates whether being a medical doctor is STEM. No one debates whether paramedicine is STEM. But nursing, the largest healthcare workforce in the United States, remains in limbo, not because of evidence, but because of narrative. Science at the bedside. Most scientific work happens in labs. In nursing, the lab is the bedside. Abram emphasizes that nursing integrates life sciences at every level of practice. Think about a routine assessment. A nurse listens to crackles in the lungs. Behind that simple act is knowledge of alveolar gas exchange. It's been a minute since I said the word. And understanding fluid dynamics, awareness of inflammatory processes, recognition of infection pathways. A nurse reviews potassium levels. Behind that is cardiac electrophysiology, just like Millennium mentioned. Sodium potassium pump mechanics, risk modeling for arrhythmia. A nurse identifies subtle confusion in a patient. Behind that is neurochemistry, perfusion dynamics, differential diagnosis logic. Nurses do not just check vitals, they interpret complex biological systems in real time. That is applied science under pressure. The math that nobody sees. Let me tell you a story of a new graduate nurse. It's her first week off orientation. She is assigned to a pediatric patient. Weight 12 kilograms. Medication ordered in milligrams per kilogram. She freezes for a moment because if she gets it wrong, it's not a rounding error. It's a child, a young life on the line. She calculates, recalculates, double checks the safe range, verifies concentration, program the pump. That is dimensional analysis. That is ratio reasoning. That is error probability mitigation. Zhu et al. Found that integrating STEM-based mathematical reasoning into nursing education significantly improves clinical thinking because nursing math is not theoretical, it is consequential. Multiply that moment by 4 million nurses in the United States. That is a workforce practicing quantitative reasoning every shift. Technology and informatics. Engineering in scrubs. When people hear engineering, they picture bridges, but engineering is about systems. Hospitals are among the most complex systems in the world. Consider sepsis protocols. A nurse notices delayed antibiotic administration. She brings it to a quality improvement meeting. The team redesigns the workflow. Door to antibiotic time drops, mortality decreases. That is systems engineering. Or consider fall prevention, risk stratification, environmental redesign, alarm system evaluation, data tracking, and process auditing. Engineering is not always steel and concrete. Sometimes it's safety checklists and process flow diagrams. Nurses are often the first to see where systems break and the first to address them. Now, as we go into the digital frontier, healthcare is now a data ecosystem. Electronic health records, clinical decision support, AI-assisted diagnostics, remote monitoring. Nursing informatics is a federally recognized specialty. Nurses help design charting interfaces, alert thresholds, workflow integration, data dashboards. They translate between human physiology and machine logic. That is technological fluency. That is systems integration. Nursing science. There is a myth that nurses apply research but do not generate it. So this is a false assumption. Cashin and Prickler describe nursing science as advancing biological understanding alongside patient-centered care. Nurse scientists conduct NIH-funded research in genomics, epigenetics, symptom science, chronic disease prevention, implementation science. Dreisbach et al. Made a direct call to action. nursing science should be federally recognized as a STEM degree because it all meets the criteria, not symbolically, but through methodology. So nurse practitioners actually deliver outcomes that prove it. So STEM disciplines produce measurable outcomes, correct? A landmark study in medical care found that nurse practitioners provide primary care quality comparable to physicians among Medicare patients. Comparable outcomes, comparable safety, comparable effectiveness. These things are not anecdotal. This is peer-reviewed evidence. Outcomes reflect scientific vigor, and nursing qualifies. So I say all this, but why does it matter? So let's move away from theory to consequences. STEM classification affects federal funding eligibility, scholarship access, workforce pipeline programs, immigration, and visa pathways. Here explains how STEM designation shapes national workforce systems. Moore et al. Links STEM inclusion to increase diversity in professional fields. Smith reminds us that nursing's historical marginalization is tied to gendered and racialized hierarchies. When we exclude nursing from STEM, we reinforce those hierarchies. Recognition is not vanity, it is structural equity. So, let's go back to 3:17 a.m. Let's go back to that hospital room in the early morning. The oxygen saturation that dropped, the nurse who intervened, the crisis that never happened, the moment that will never make headlines. It won't be published in physics journals, but it requires scientific reasoning, technological fluency, engineering logic, mathematical precision. It required STEM, and it required nursing. So here's the verdict. When a nurse titrates a vasopressor to stabilize blood pressure, that is not just caring, that is applied pharmacodynamics. When a nurse identifies sepsis before the lab calls, that is not intuition, that is pattern recognition grounded in pathophysiology. When a nurse redesigns a workflow that prevents infections, that is not helping out, that is systems engineering. When a nurse calculates a pediatric dose at 3 a.m., that is not routine. That is mathematics with life on the line. And yet, we hesitate. We hesitate to call it STEM. Why? Because somewhere along the way, we decided that compassion and computation could not coexist. We decided that empathy and engineering were opposites. We decided that if a profession is relational, it cannot also be rigorously technical, but that is a false choice. Nursing proves that you can hold a hand and analyze a blood gas. You can comfort a family and interpret complex hemodynamics. You can wipe away tears and rewrite safety protocols. You can care deeply and calculate precisely. In fact, that combination is not a weakness. It is the future of STEM. Because the future is not cold. The future of science is human-centered. The future of engineering must account for lived experiences. The future of technology must serve people, not just systems, and nurses have been doing that all along. So this is not just about classifications. It's about visibility. It's about funding. It's about who gets invited to the table when STEM policy is written. It is about who gets counted. It is about who gets valued. If STEM is defined by science, technology, engineering, and math, nursing qualifies. If STEM is defined by measurable outcomes, nursing delivers. If STEM is defined by rigor, nursing exceeds it. So let's stop asking whether nursing belongs in STEM. Let's start by asking why it took this long to recognize it. Because at 3:17 a.m., in that hospital room, when oxygen drops, when alarms sound, when seconds matter, no one in that room is wondering whether the nurse is STEM. They're just grateful that they're there. Nursing is STEM, and it's time the world said it out loud. Thank you.
Oh,
And of course,
very
my
good.
references if you want to see it.
Yeah, thank you. Well, it
Of
was
course.
great presentation. And yeah, that's true. I haven't realized this was a thing until your presentation, actually. I just realized that it is STEM. Indeed.
Yeah, it's something that not a lot of people recognize because nursing by and large has been stereotyped into, just an outfit or some sort of kink. It's much more than that.
Yes, absolutely. It is. It was considered like more of a helping kind of deal, but really is. There is a lot of STEM. There is a lot of decision taking, and not only decision taking, but decision taking based on other things. Yes,
Hmm.
very interesting. Yeah, you answered almost all the questions I have made before
Oh,
in the
really?
presentation. Yeah, but I have one that is a little bit off, but you know,
Sure.
just for asking, with the advance of AI in a lot of fields, I do wonder how does AI kind of helps uh, maybe makes an negative impact in nursing. What are your
So
takes on
AI, at the end of the day, it's supposed to be a tool, not the answer to the to our problems. So, for example, there was an article that was out recently. That I think I still have it saved on my browser. Actually, now that I mention it, yeah, Chat GPT Health, how disastrous it has become. It was released by Nature.com recently. It says how most Chat GPT diagnoses got it all wrong, and they didn't escalate the care that the patients needed appropriately. So when we become so dependent on AI to make decisions for us, we really do lose that technical knowledge, that learned experiences, that intuition, and sometimes it's just gut feeling. Um, when when we rely too much on AI to solve our issues. So yeah, it's would we use AI on the floor? I believe so. It's coming. I mean, it's even right there in our electronic health records right now as we speak. Um, it's a very useful tool in terms of trying to get an overall picture of the patient, of what to expect, especially in terms of algorithms of how to approach their care. But at the end of the day, the clinical decision making needs to be up to the providers. It's up to the doctors, the nurses, the therapists, the technicians who all work with the patient. And AI simply cannot do all of that because nursing is a human thing. It requires a human touch. Well, not just nursing, but healthcare, really.
it? Yes, exactly. Well, thank you very, very much for the presentation. It was really, really good.
Of
Thank
course.
you very much.
Glad to share.
Okay, now next one is Ursha. If you can, please.
Yes, give me 1 second.
Okie dokie.
Okay. Show. Share screen. And is that visible to everyone?
Let me see. I'll bring it up. And yes, whenever you're ready.
Sorry, give me 1 second. I apology.
Oh yeah. In the meantime,
So,
we
so sorry. I'm ready.
Oh, okay, okay. Just one quick side discussion we are having in chat is the also professors, right? Professors are treated as a STEM as well. Yes, and that's pretty weird because you are teaching people who will be making STEM, or who will be acting upon a STEM, but you are not considered STEM yourself. Yeah, that's pretty weird. I agree with that. Yes, Ursula, yes, whenever you're ready, you can be.
Okay, thank you. All right, hello. Well, welcome. Thank you so much for having me. Today, we're gonna do something very basic, very simple. We're gonna talk about how to build a pen from scratch, and showcasing how, despite what you think, geology is in everywhere and everything in your life. So, I want to start off with do a hypothetical. If you look around where you are right now, I want you to look at everything, and I do mean everything from the tables to the screens or the headphones you're using to the seats you're sitting on, and think about how much of that do you think is actually grown, as in like it was planted, grown, harvested, and then I want you to think about that percentage. Whatever percentage you think that is, the other half of that has to have been mined or taken from the earth. So there's a saying here in geology that is, if it is not grown, it is mined from the earth. You start thinking about everything, and I do mean everything in your life, not just the complex electronics and so forth, but the very elements that are part of that. The very elements and so forth had to have come almost, if it was not like organically grown, had to have come from mining the minerals and so forth. And those minerals and elements would not have gotten there without the work of geology and a mixture of time, landscape changes, biology interaction, everything, and millions of years and so forth. And so I wanted to take a very basic thing, one basic thing that we all have used for, and we're going to talk about how to get a ballpoint pen. I'm sure you have all used this before. This is known as the Bic pen or Bic Crystal. It was, introduced in 1950. It's basic design. It's been used around the world. Hundreds of billions have been sold and used. I imagine every single person here has probably used this exact type of pen. We are going to be looking at how the different parts of the based on the material, from the metal ballpoint and tips to the plastic parts and body to the ink itself. Each part had to have been created under a geological formation that has took time, pressure, heat, interaction with water and biology for it to form. So let's start off with the metal tip. So starting off, the metal tip itself is made of a material called brass. If you've heard of brass before, in fancy, it's one of the more common alloys, as in it's a mixture of two metals. In this case, is a mixture of copper and zinc. We're going to start off with copper. Copper, you know what copper is. Copper is the sort of goldish, brownish material. You see it in electronics, you see it in cars, you see it in like plumbing. It's one of the most mined and crucial metals we have taken on Earth. And to get that mineral, you have to mine it. So there is a material known as, one sec. So how do we get that copper? Well, it has to we're going to skip over some steps. First, you have to form a universe. So there's a Big Bang, then a solar system, and then, stars have to die and so forth. And then we get a solar system, and all those elements have to come together to form planets and so forth. And all that planets have to cool down and so forth, and yada, yada, yada. We're going to skip over about 14.6, about 10.3 billion years to about 4.5 billion. We have the Earth. All those metals that were created are gathered in the Earth, part of the mantle and part of the inner mantle and core. And over time, through plate tectonics, through movement, we get those metals coming up. For example, copper, along two tectonic plates, for example, you might have seen this in like school, where plates will go underneath each other. For copper in particular, that material can interact with As it goes down, it gets melted down and interacts with part of what we call the mantle, which is the second layer underneath the Earth. When that mixes, that mantle material is often rich with a lot of metals, including copper. This material gets made up into like a magmatic soup that's like the consistency of, if you're familiar with what silly putty is, or like a very plasticky kind of clay like texture. It's very stingy and so forth. You've seen like lava and so forth. It's like that forbidden like marshmallow type material you want to touch, but you know you can't. Take it from me, you don't. That material is floating in a magma sort of body. That body, so in this case, this magma body never erupts into like a. Sometimes it can erupt, but in this case, it doesn't erupt. This is referred to in geology as a plutonic. This is how you form the magma sort of stays put and cools inside the Earth, becoming slowly more solidified and so forth. Eventually, as this material is filled and so forth, very slowly over time, as more and more sort of elements get crystallized and sort of form, and it cools down slowly over time, that some of the metals get leached out until you start getting richer and richer and richer copper, richer and richer metals, including copper. This forms at the very end, at the very last layer, you'll see a very rich, you'll see interaction there. Those interactions will form this copper layer around here, this ore zone where the copper is super high, in this case 1 to 3%. That's very heavy copper. And this is where we get these deposits. We refer to them in this industry called porphyry, or a copper porphyry deposit. We call it a porphyry because it is a plutonic mineral. We refer to it because the texture, or how the rock looks, has these larger crystals inside, like a smaller, we call it the background mineral, the smaller ones, like a matrix. The matrix is like tiny minerals you can barely see, and then there are larger crystals you can sort of see. Eventually, this is how we form. So the copper is not just copper of itself. It bonds with other elements to sort of form stable crystals. In this case, for copper, one of the most common minerals for that we mine copper out of is a mineral called chalcopyrite. It is referred to as a copper sulfide. So it's a copper that is mixed with some sulfide elements to sort of form a crystalline structure. We usually these sort of the porphyry large magma deposits can often have quite a bit of sulfide in this case, and so we take that copper, or take that mineral. This is a pretty example of it. You can see these sort of cubic golden kind of. When you think of fool's gold, there's a related mineral that's called pyrite. That's an iron sulfide, and you can usually find it in the same location. This is the mineral you would take, and then through mining, chemical breakdowns, both chemical and physical, like breaking and so forth, you can separate the sulfide and get the pure copper that you need, and that's how you get the copper that you need. So we did all that, and that's just the copper. What about the other half? What about zinc? So zinc is the other crucial mineral that you need to create Basque. So zinc can form in similar situations. However, they form in a different kind of deposit. This is known as a sedimentary exhalative, or a SEDEX deposit. These are usually filled with superheated water that are filled with metal. So think of like, you've seen like maybe when you think of like hydrothermal, you think of like geysers you may have seen in Yellowstone. Those water is filled with a lot of minerals coming from a magma body or so forth. In this case, these minerals are interacting, and then will interact, and slowly through faults and cracks in the earth will slowly come up and then bubble up, and get this mineral rich water will interact with the ocean and suddenly deposit everything and slowly form like a basic layer. When we see like something that just forms a horizontal basic layer, we refer to that as sedimentary. So, if you have ever seen those pictures of black smokers, like underneath where you see like the smoke, black smoke coming out that's like on the bottom of the earth, that's where minerals like zinc, lead, and iron, and other metals are forming. And that's not the only way. You can have example where you have these are known as a volcanogenic massive sulfide, or VMS. So these are like volcanic. That means that there was some eruption, there was some material that was interacting. Usually it's below ground. It's usually below ground or in a sea floor. When that lava interacts with the ocean, it immediately freezes. We call it, the term is quench, where it essentially immediately crystallizes. It's no longer like super hot and so forth. When that happens, these rich minerals are formed that form, and they create these metal-rich materials of things like zinc, iron, copper, and gold and silver even. So usually, again, we have to find the mineral containing it. In this case, this is sphalerite. This is a common zinc mineral that we use to get zinc out of. It's a mineral that's like chalcopyrite, where it's a sulfide. So it's zinc mixed with sulfur to form this stable crystal. This sort of, and you can kind of always tell. You can actually see those dark gray mineral is the sphalerite, and the lighter gold one is the chalcopyrite. So oftentimes when you're mining these deposits, you're getting many different metals from iron, copper, lead, zinc, even heavy metals like gold and silver. So we have our brass, and we have that. What about the ball? The ball is made from a material called tungsten carbide, which is a mixture of carbon and tungsten. Well, that means we have to get tungsten. Tungsten's a very important, super hard, like tough metal that we need for lots of things. But in order to make our pen, we have to find some tungsten. Well, if we go back to our first example, the porphyry deposits, at the very edge of where the magma meets, like the general, what we call the source rock, the rock that sort of surrounds the magma, there is that rock is superheated by the hydrothermal fluids, the mineral-rich water, and also by the magma itself, and it actually causes them to change or metamorphize over time. This forms a deposit that's known as a skarn. So when that interacts, it interacts and alters the rock and the minerals in it, because it sort of melts down and it comes together and forms new minerals. Oftentimes, that mineral-rich water and magma will form new minerals in that source rock, and it will form this band where you can find mineral-rich rocks. In this case, for example, with tungsten, if you think of granite, you'll go around and look at granite. You'll see big granite deposits. You might find at the edge of those deposits locations where you'll see long, we call these long tendrils that have following cracks in the surface of that stable, that source rock. We call them dikes, and inside there you can find rich metal-rich minerals. In this case, for tungsten, we are looking for two specific minerals. One called wolframite, which is a tungsten oxide that mixes with iron and manganese to form these stable minerals. If you've also ever heard from different parts of the world, you might have heard tungsten referred to as wolfram. This is where that name comes from. It comes from wolframite. Or it also forms another mineral called scheelite, which is similar to it's another tungsten oxide, but instead of iron or manganese is the other mineral or other element part of it, you get calcite to form these. So we mine those materials. We got all that. We got our metals. So now we have to form our plastic. But wait, what about the carbon? We need that for our tungsten. And so how are we going to make the plastic? Well, we need to look for carbon. What is the best type of carbon? this is where we get the term fossil fuels. The fossil fuels, despite what you may have heard, is not made of dinosaurs. It's made of material older than the dinosaurs. There is a period of time known as the Carboniferous. In some parts of the world, it's called the Carboniferous. In the United States, the period is referred to as the Mississippian and the Pennsylvanian. But this is a period that existed far before the dinosaurs, roughly 300 from 350 to 300 million years ago. So before the dinosaur, the world and the cover was covered with these large swamps and wetlands and peat bogs, lots of material and so forth that very slowly over time just sort of accumulates. As it gets over time, as that material gets pressured under both like newer layers and heat and so forth, it slowly closes. That material doesn't like decay or something. It just gets squished more and more and more until you're left with this dark black material that you and I know as coal. Well, so we're gonna need coal. We usually get that. That's our carbon for our little steel tungsten carbide ball. What do we need to form? Well, to get the other materials for our pen, we need to look for oil. Oil is like coal. It's formed from microscopic. It's formed from life forms. In this case, like algae and so forth, and it's oceanic. And it slowly accumulates again, gets heated and pressurized, turned into that goop, that sort of goop you know as oil. That becomes oil. And then slowly over time, as that's superheated, it'll slowly migrate up into higher layers until it finds a layer that is less porous. So it goes through things like sandstone and limestone very easily, but it'll hit something like shale, which is very thick and you can't get through it, and it'll cap and it'll hold there. And in that, that's where you can find oil, natural gas, and petroleum, which is where that's how you mine oil and gas. That's how you like extract oil, natural gas, everything like that. And with that oil, so now we have the oil. That's where we take the oil and petroleum, we refine that into the plastics, into the long polymer plastics that we need to form the rest of our pen. So we need our pen cap, or different types. In this case, the main body is made of polystyrene, like the stuff. It's mold injected, like the polystyrene, like peanuts you probably use in packaging. And then the other parts is made of propylene, which is a more harder resistant plastic. Even the ink itself requires something from the earth. Well, the ink has some origin. The blue ink you will use and so forth comes from a dye called phytocyanine blue. This is a chemical that is synthesized from mixing copper salts, which actually helps get its blue color, and a molecule called phytocyanines, which forms as a byproduct of benzene, which is a natural component of petroleum. So, after all of that work, after millions of years in work, after long labor and extraction, refining, and so forth, we get the blue that we need to use the pen, and it's formed. This is how we get a pen. So the goal of this talk was to bring forth the idea that geology is not a static. It is not a static. It is not just looking at rocks. It's just seeing them what they're. There's a story behind every single landscape you see. There's a story behind every single material and piece that you every single thing from their phone. Everything has to have been created, not just through the natural process, but through human processes, labor, innovation, construction, even the more negative parts of humanity, from war to resources. All this influenced by a dynamic world that is the world around you. So I hope my goal here was to let you know and start thinking about how your world is a lot more alive than you think it is. A lot more live and dynamic. And that was my talk. Thank you so much.
Thank you very much.
Yeah.
That was an awesome talk. Yeah. And you definitely did your objective. You definitely reached it. Absolutely. Oh, yeah, I would never guessed. So many things are involved in making a pen.
Yes, so much. Is there any questions?
Yes, there are some questions. Okay, let me get.
Oh. Shoot, I'm sorry, I
yeah.
didn't mean to turn that off.
Oh, no worries. Okay, so I have some questions from Turant. Does copper and zinc being next to each other on the periodic table make them harder to combine?
Yes, this is actually more of a chemistry question.
Yeah.
Because essentially the one difference between them is that you need, if you go back to chemistry, you need to form like ionic bonds. It needs to find like a negative and so forth. Copper is usually known as a cation, so it kind of has a small positive charge. I'm sorry, if I'm all chemist, I apologize if I'm screwing this up. It needs to find like an element that will bond with it to cancel out that charge. In this case, zinc and copper are both cations, so they have that positive charge and it needs the negative. That's why it bonds so well with sulfide. But given that the fact, and that's why you will often find those together, is that usually these metals are still in the similar, they're also similar in, like, they're close enough that, you usually find them along with other metals in that same area of the periodic table. But they won't bond with each other. So they need that negative anion. That's the word I was looking for, to bond with it.
Yeah, makes sense.
I don't know if that answered your question, but
I think it does. The thing is, next edition, getting a chemistry. I got the memo. Okay, one more question from Sidion, asking if is copper nitrate the one that formed those pretty blue crystals in the lab? Oh, I guess they are asking if there are there any other ores that can have that blue crystal pattern kind of deal?
oh, absolutely. Yeah, oftentimes you might actually know. You might see things. Copper is formed in lots of different minerals. Oftentimes they will be less. They oftentimes, if you remember from chemistry, if you ever burned some copper, it actually gives off more of a greenish color sometimes, and sometimes you will see that in minerals. So there are some examples of minerals that are often other copper minerals that will give it a kind of will give it a color. There's a the one that's coming to mind is a more of a there's something called malachite. It's a hydroxide mineral, meaning that will form in like caves and things like that, and it has this very pretty greenish color. That being said, there's also a mineral called chalcocite, and that one usually it's not as dark, not as like blue as a nitrate, but it's like a dark blue, like a dark grayish blue and so forth. So usually that's why it's such an, or there's another one called covellite, which is a rarer version of copper sulfide. Instead of having copper and iron, it's just copper and sulfur, and it has this brilliant blue mineral. So oftentimes that's another way of identifying minerals when you're trying to survey or look for potential mining locations. Sight and color and everything can be indication of that, and that blue and green can affect the chemistry and so forth. It's the same way how sulfur, you can often identify sulfur by its brilliant yellow color. It's why like the chalcopyrite has that kind of yellow color, because there are two sulfurs that gives the color sort of stronger. It sort of it scatters light with more off the sulfur, so it gives the more yellowish color that you see. I might I apologize if I'm a little bit iffy there with some of the details on the chemistry. It's been a while, but
Okay.
I hope that answers your question.
Yeah, I think there's no worries, no worries. Okay, yeah, I believe that was it. Yes. Okay, Nico, do you wanna make your presentation now?
Yeah, hold on. Let me share my screen.
Okay. And also, thank you, Roche. Appreciate the
Thank you so
presentation.
much.
Thank you.
Does that work? Can you see that?
Yes, wait a second. Let me just adjust some things up. Okay, there we go. Can begin.
Okay. All right. Thank you. And hello, I'm Nico. I'm the bacteria scientist VTuber, and I'm going to be here talking to you guys about bacteria, the microscopic chefs, and how they shape things that we eat. And this is going to be quite an intro level because you can really go deep dive into food science and food microbiology, but I think it's still a very cool topic to just introduce to you guys, especially if you aren't super familiar with microbiology to begin with. So, to begin with, let's start with what even is a bacteria, if you're not familiar with that. If you're not familiar with my little species, bacteria. So, at its core, a bacteria is just a single cell. There's no nucleus, there's nothing fancy going on. It's just a tiny little self-sufficient little unit of life. And when I say tiny, it's really tiny. We're talking 1,000 times smaller than a grain of sand here. But don't let that teeny tiny size fool you. These guys, including me, are everywhere. There are roughly 10 to the 30th bacteria on Earth. That's 30 zeros, and your gut alone has about 38 trillion of them right now. So, you're kind of like the home to a whole bunch of bacteria, if you didn't know that. We also reproduce incredibly fast. One single bacteria in 8 hours can become about 16 million. So, that you can see why we're kind of taking over the world. And even though sometimes bacteria can sound kind of scary, I know you think of bacterial infections, you think of all the nasty guys causing so many diseases and problems. A vast majority of bacteria are actually pretty friendly, where they're symbiotic. It's only about less than 1% of bacterial species that actually cause diseases or kind of pathogenic harm. And so on the right, you can kind of see a closer look of what a bacteria might look like if you slice this open. So that includes ribosomes, a DNA, cell wall, pili, flagella. Very simple, but we're able to do just so much. And before we get too much into what they actually do, there is the topic of food science itself. So food science is a topic I really liked, and it was something I actually wanted to study, but ended up not pursuing myself. So food science is a multidisciplinary field. It's just a fancy way of, it's so many different sciences that are part of this. They use chemistry, biology, engineering, and nutrition to kind of study and ensure the quality and safety of the food we're eating every single day. But it's not just cooking and food related. It's understanding how ingredients interact on a molecular level. How do we prevent foodborne illnesses? How do we keep food fresher longer? How do we make it more nutritious? And so the food science research can get pretty wild, and food microbiology plays just a kind of a teeny tiny role in it, as you can see here. Food microbiology I thought was the coolest topic, but there's just so many aspects of food science that you can actually really dive into. And so today's topic is really going to get into how our little bacteria guys fit into our food production. So, a bacteria is probably responsible for some of your favorite foods if you aren't familiar with that. They transform so many simple ingredients into completely different products. Milk can become cheese and yogurt thanks to bacteria. Vegetables can become kimchi and pickles. You can turn sweet tea into kombucha. Dough can become sourdough. These changes happen because bacteria can chemically modify sugars and other nutrients in food, which can change the flavor, texture, as well as help us with preservation of these foods. And we're going to get into more details of how that exactly works. It's just, I want to make sure you understand there's a lot of food here. That this is a simple overview of the amount of food bacteria actually convert. But you should thank your bacteria friends, for helping you guys out. So to understand how bacteria actually create these foods, you have to kind of understand what fermentation is. Fermentation is this engine behind most of the foods we saw. The concept is pretty simple. Bacteria eat the sugars and starches, and as a byproduct, they produce metabolic products such as acids, gases, and alcohols. These byproducts transform the original foods such as flours, sugars, into perhaps fresh sourdough bread. And it's important to know the bacteria aren't doing this for us. We're not this is just, they're metabolizing the food for energy the same we do. We're just happening to benefit from that extra step of that. What they produce as a byproduct when they need energy is actually useful for us. Humans were able to, figure out how to harness that side effect, which is pretty cool. And so one of the three key outputs of bacterial fermentation, lactic acid, carbon dioxide, ethanol, acetic acid, these are kind of the big three players that you see for fermentation and why we're able to have so many nice foods thanks to bacteria. And I wanted to also go deeper into the three big ones. I think bread, yogurt, cheese, those are some of the most delicious foods out there. And so it'd be fun to kind of understand how bacteria transform these raw ingredients and turn them into the delicious things that we eat. So first, sourdough bread. In sourdough, bacteria like L. sanfrancensis. Okay, I know I said I'm a bacteria VTuber, but I really suck at pronouncing bacteria names. It's just hard. Don't get at me. They consume sugars from the flowers. As they metabolize those sugars, they are producing lactic acid and acetic acid. Those acids give sourdough bread its tangy flavors and also change the structure of the dough. Meanwhile, there's wild yeast also producing carbon dioxide, which makes that bread get that fluffy, nice texture that we like. So, we have a partnership here of the microbes. It's not just bacteria. There's also bacteria and yeast working together here. Bacteria giving it the flavor and chemistry, and yeast kind of handling it to make sure it has structure and bounce and niceness of bread. And yogurt. So for yogurt, we first have to heat up the milk to remove competing microbes. We don't want any of the nasty guys there. We only want the two nice bacteria that we know that are going to work together to create the tanginess. So we have L. bulgaricus and S. thermophilus. They're added together and they work together to ferment lactose into lactic acid. As that acid builds up, the milk proteins start to denature or break down, and they thicken, turning liquid milk into yogurt. You can really mimic this effect yourself if you add something like lemon juice to milk to make buttermilk. It gets all creamy and kind of not as loose as a milk as it is usually. And so when you create that signature tang comes from compounds like lactic acid and acetaldehydes. And that's how you get delicious yogurt. Finally, aged cheese. Now, here's the primary bacteria acidify the milk to form curds. And then they remove what's left over, and they add even more bacteria on top of that to take over during aging. And this is over the course of months or years. And they slowly break down proteins and fat into smaller molecules. And that breakdown includes things like butyric acid, sulfur compounds, amino acids, and that gives it all these cheeses their unique flavors and also their unique smells. If you don't like the smell of cheese, you probably can attribute that to the butyric acid that gets created or the sulfur compounds. So I like that smell and all that taste, but if you don't like it, you can blame the bacteria. And this is just another closer look at some of the actual chemical mechanisms that go into fermentation. So for lactic acid fermentation, you have glucose, which is the structure of C6H12O6. Just sugars are just carbon, hydrogens and oxygens, and that is transformed into an intermediate pyruvate, and that's now turned into yummy lactic acid. Similarly, acetic acid, this is one that requires oxygen, that turns alcohol, taking the oxygen in the air, turns it into amazing acetic acid. I could show deeper into the pathways, but there's a lot of pathways and molecules that happen, and I think that would have taken too much time, so I'm always happy to answer questions if you are interested in more of this chemical pathway section. So it's also good to know that it's not just like bread, cheese, and yogurt. That's the most simple part of bacterial fermentation. There's many different aspects. There's things such as precision fermentation that bacteria are part of here. This is like kind of new science. I'm not super familiar with it myself, but as I was doing research, we can use bacteria to create actual animal-like molecules like dairy proteins, heme ions, egg whites, all just from fermenting bacteria, as we normally do for sourdough and other simple foods. Pretty interesting. We also use bacteria for things such as vitamin and probiotic production, flavor chemicals like food enzymes, colors, food preservations, meat alternatives. There's a whole lot of things that the bacteria are doing here. Not just our bread, cheese, and yogurt, but they do provide delicious bread, cheese, and yogurt. However, it's important to know not all bacteria are good. We talked a little bit about how less than 1% of bacteria do cause harm, and unfortunately that does exist on our food. And that's important to remember, that we have to be aware that not everything is always going to be great. Some bacteria are going to create harmful toxins and compounds that will hurt you, and you have to be mindful of what you're eating. So, for example, there's Salmonella, E. coli, Listeria, Campylobacter, all the things that could potentially give you an owie tummy. They all work in a pretty similar manner, all differ just a little bit though, and that's usually invading your immune system and triggering inflammatory immune responses because of the toxins that they're producing, and then you get the owie. And this is because, and it's important to also know how this happens with the evil bacteria, is because if you leave food out, they will grow. If you are not careful with food safety, bacteria do like to grow on that food. There is important part is looking at the growth curve of bacteria. There's the lag phase, log phase, stationary phase, and decline phase. So you can leave food maybe up to like 2 hours, but after that 2-hour phase, you need to be careful. You are allowing bacteria to grow exponentially. There is a lot of guys growing on that food right now in 2 to 8 hours, and then as they're growing and taking up all that spot, they are dropping so much toxic waste onto your maybe once delicious meal. At that point, this is the stationary phase. We are running out of actual nutrients. It's becoming too crowded. There's so much waste now, and the bacteria are just dying. They can't handle it anymore. There's no more room for them. So while the bacteria might be dead, there's a lot of inflammatory waste on your meal, and that's going to cause you to get sick. To stop the evil, you got to be mindful of food temperatures. You have to avoid this danger zone, the 40 to 140 degrees Fahrenheit. That's the bad zone. Do not leave your food there for a long time. This is also a reason why cooking is important. Cooking allows us to destroy and kill bacteria, but mind you that killing the bacteria does not exactly get rid of the waste. If the waste is there, you are not going to, unfortunately, get rid of that. You're going to have to throw out that meal. And then similarly, if you freeze and store your food in a refrigerator or in a freezer, you're preventing that growth from happening. But if that growth was already there, it's our food now. Sorry. guys. Sorry, humans. That's our food now. And there's food safety systems to keep in mind. This is really more for like professional, like industrial level cooking, but it's always good to keep this in mind even when you're cooking at home, and also if you're eating from somebody else's kitchen, just be mindful. Hopefully they took extra caution with food safety systems. So next time you eat, you should think about who cooked it. It might be me, the bacteria. And thank you. That's it for me. I'll have any questions.
Thank you very much. That was an awesome presentation. I love the bacteria, guys.
Thank you. Thank you.
So yeah, we have one question from Sidium, asking if we can get insulin from bacteria as well.
Yes, you can make insulin from bacteria. Usually we use E. coli for like genetically engineering purposes. There's a lot of biohacking labs, which are usually individual labs not associated with an like a company or a school. They've been known to produce insulin themselves and sell that for cheaper, at least in the United States. It's pretty cool.
Okay. Yes. So I have some more questions for my own now. Yes. There's a thing when we have an unbalanced gut microbiome. Can you tell us what's going on with the good bacteria when that happens?
Oh, of course. I was considering talking more about the gut microbiome here but I was like, oh my gosh, it's going to get so long. But yes, so our gut microbiome, if you're not aware of that, that's where we have this wonderful balance of bacteria that are helping break down the meals and our food that we're eating. And then we have a very delicate balance of making sure we keep the nice bacteria that only want to help break down the food and not cause any harm, and make sure the population of bad bacteria that want to cause inflammatory damage, release a lot of inflammation, cause harm to us are minimized. And sometimes this balance can get disrupted, especially when you take something like antibiotics, because antibiotics don't really understand. They're not saying, oh, you're good, you're bad, you're good, you're bad. They're wiping out your whole microbiome. And so when you take that and you wipe out your whole microbiome, you could end up getting a population of only bad bacteria primarily, and this can cause a disbalance, and that can lead to so many uncomfortable issues like bloating, diarrhea, pain, terrible suffering. It sucks.
Yeah. It's all good when you have your good friends with you, but when they get destroyed by an antibiotic, not so good.
Not so good, not so good. You want the good guys. It's important to keep the good guys with us.
Yes. Okay, yeah, I believe that was it.
Thank you.
Yes. Thank you for the presentation. Thank you all of you guys for the presentations. I'm going to take us back to the symposium. Oh wait, we have one missing. Yeah, we are here. Okay, yes, that was it for the symposium. Thank you all for the presentations. It was very good from all of you. And
Thank you.
Thank you.
Thank you so
It was
much for
fun.
hosting and
Oh.
organizing.
Thank you.
Yes.
Thank you guys very much.
Thank you for the invitation.
Thank you guys very much for taking part of it. Again, so the intent of the VTuber Symposium, the intent of all of this, is for us to show that VTubers can also do many of things. We have people that do gameplays, people that do live chats, reacting, and all of that. But you also have many scientists that are also VTubers, and that they can show content outside from just the normal VTubing things that we do. So yes, this is the idea of the symposium, to show to the world that VTubers can be much more. They can do almost anything they want, really. So yeah, so that's the whole idea of the symposium, and I think we have achieved that here. and I'm very, very proud. Thank you very much for the presentations again. And this was an amazing symposium. I hope you guys all liked it. The questions also were very good. Thank you very much for the chats. And that's it. That's the end of our symposium. Again, thank you very, very much for being here. And I will see you in a next time. Thank you very much. I see you in maybe a next time. And bye bye. Say bye, guys.
Bye, everyone.
Thank you.
Bye.
Bye bye.